Welcome back. With this video, we are beginning a segment on internetworking. We have learned how to network two endpoints by connecting these with a link. In this segment, we will understand how to build larger networks. The term internetworking, as we have discussed before, refers to interconnecting different type of networks. And we are going to begin this segment with switching. In this video, we will get familiar with switching and forwarding, and we will know three different approaches of switching. First one is called datagram switching, the second is virtual circuit switching, and the third is source routing. We are going to discuss all three of them. By the end of this video, you would know what is a switch, and what is switching, and what is forwarding. And you would know how a virtual circuit is set up and how does virtual circuit switching compare with datagram forwarding. And finally, you will know how does source routing work. What is a switch? A switch is a multi-input, multi-output device which transfers incoming packets to one or more output ports. Here is an image of a switch. You can see that it has 16 ports, 8 ports at the top and 8 other ports at the bottom. All ports are labeled with numbers. And on the right side, this shows the symbol for a switch. Although we can attach hosts to these ports, we can also attach switches to these ports. By doing so, switches allow us to build ever larger networks. So that's what it says here. Even though a switch has a fixed number of inputs and outputs, larger networks can be built by interconnecting a number of switches. Here is an illustration that shows that we can build larger and larger networks by interconnecting switches. So here is a switch that connects 3 hosts, but then we connect another switch to it, and then this switch would have a bunch of ports, so we can attach hosts to it, and we can further connect another switch to one of its port, and then this switch in turn can be connected to other switches and so on. This network configuration where hosts are connected to a switch via point-to-point link is called a star topology. Note that in this topology, the hosts are not connected directly to their peers. They only connect to their peers through the switch. Given the same bandwidth, switched network gives better performance than shared media networks. Why? Because in shared medium networks, the bandwidth is shared by hosts. So suppose multiple hosts are connected to a 10 Mbps Ethernet segment. Since all the hosts share the bandwidth, as a result, the maximum data rate at which any one host can transmit continuously must be less than 10 Mbps. However, since every host on a switch network is connected by point-to-point link, it is possible that multiple hosts will be able to transmit at the maximum data rate, provided of course that the switch is designed with enough aggregate capacity. Since switches allow isolation of traffic, adding new hosts does not necessarily mean that the hosts that are already connected to the network will get worse performance. And therefore, switched networks are more scalable than shared media ones. A switch runs appropriate data link protocol to communicate with each of the connected nodes. And the term switching refers to receiving incoming packets on one of the links and transmitting them on one or other outgoing links. A switch runs appropriate data link protocol to communicate with each of its connected nodes. The term switching refers to receiving incoming packets on one of the links and transmitting them on some other link or a set of links. A switch determines the output ports on which to forward packet by looking at the header to make that decision. We are going to see three approaches of switching. Two of them are common approaches, and then there is another approach that we will also discuss. The common approaches are datagram or connectionless approach and virtual circuit or connection oriented approach. And there is another approach that's called source routing that we are also going to discuss, as I said. We are going to make two assumptions. The first is that each host has a network-wide unique address. We have seen one such example that was Ethernet MAC address. However, it could be any other addressing scheme. All we require is that every host has a unique address. And we are just going to denote the addresses by letters like A, B, C, D, and so on. And the second assumption is that there has to be some way to identify input and output ports of each switch. For that, we could use numbers, as I showed in the image of a switch in the beginning of this video, or we could use the name or address of the host that is connected to different ports. However, we are going to use port numbers in the rest of this discussion. Datagram switching represents connectionless switching approach. This approach is rather straightforward. So in the case of datagram switching, a switch makes the forwarding decision based on the destination address that is present in every packet. And it has a forwarding table which is used to make the forwarding decision for a given packet. Here is an example of forwarding table. So in this example network, we have three switches: switch 1, switch 2, and switch 3. Hosts A, C, and D are connected to switch 1, host E and host F are connected to switch 2, and the rest three hosts B, H, and G are connected to switch 3. And this is the forwarding table of switch 2 at this switch. And as you can see in this diagram, right, to reach host A, switch 2 has to forward the packet on its port number 3 so that it goes to switch 1, which in turn is going to forward this packet to host A. And therefore, for destination address A, the forwarding port number is 3. Can take another example of host B. As you can see, host B is connected to switch 3, and switch 3 is connected to switch 2 at port 0, and therefore to send any packet to host B, this switch has to forward that on its port 0, and that is reflected in this forwarding table. And I encourage you to work through all the other examples. How do we build forwarding table? And we will see that that process is called routing, and that will come in a few lectures down the road. The next switching approach that we are going to discuss is virtual circuit switching. This uses the concept of virtual circuit, and this approach is also called connection oriented switching. Note that we are using the term virtual circuit and not circuit, right? So in circuit switching, recall that the resources are reserved for each circuit that is established through the network. In the case of virtual circuit switching, we don't reserve resources. Packets are transmitted on the basis of a statistical multiplexing. However, there is a connection setup phase, and then there is a separate data transmission phase. So in the case of virtual circuit switching, first we set up a virtual connection from the source to the destination, and then we send the data. Right? So in the example that we are going to discuss, we will have this setup of 4 switches, and we will be considering a data transmission from host A to host B through this network. In the connection setup phase, a connection state is established in each of the switches between the source and the destination. And this connection state is maintained inside a table in each of the switches on the path, and that is called virtual circuit table or VC table. And this state looks something like this. So it has 2 pairs: incoming interface and incoming VCI, and outgoing interface and outgoing VCI. And what it means is that let's consider this virtual circuit table entry on switch 1. So what it means is that the transmissions from host A would arrive to the switch on port 2, because that's how it's connected to switch 1, and it would have a label, right, a virtual circuit identifier or VCI, and that label is going to be 5. And so what this table means is that if we have an incoming packet on interface 2 with label 5, then we are going to send it on interface 1 with a different label, and that is going to be label number 11. So the incoming packet to this switch 1 looks like this. So there is a 5 in the place of the circuit identifier, and then once this packet leaves switch 1, then the place of this virtual circuit identifier we see an 11, right, and this is sent via port 1, right. And clearly, as we said, we are going to always consider, host A sending to host B, and so the packets are going to go from host A to switch 1, then to switch 2, then to switch 3, and then finally to host B. So what we discussed is summarized on the next 2 slides. The first slide has the summary of virtual circuit table, and one entry in this table contains incoming interface on which packets for this virtual circuit arrive at the switch. Then there is a field for incoming virtual circuit identifier, right, that is carried inside header of all the incoming packets. And it's important to note that this pair, the virtual circuit identifier and the incoming interface, together identify a virtual circuit. And the scope of this virtual circuit identifier is link local. That means a switch may reuse this virtual circuit identifier for some other port. And then the other 2 entries are outgoing interface on which the packets for this virtual circuit would leave the switch, and then lastly outgoing virtual circuit identifier, which is potentially different identifier from the incoming virtual circuit identifier. And then as we discussed, this summarizes virtual circuit forwarding. So a packet that arrives with certain virtual circuit identifier in its header, right? So in this example, the identifier was 5, and this packet was arriving at incoming interface 2. Then this packet is sent out after replacing the incoming VCI with the outgoing VCI. So the incoming VCI is 5, the outgoing VCI is 11. So this 5 is replaced with 11. And then it's sent on the specified outgoing interface, which is interface number 1, right? So this packet is going to be sent on this interface. Next, we are going to see how virtual circuits are established. So there are two approaches. One is called permanent virtual circuit, and the other one is called switched virtual circuit or just virtual circuit. In the case of permanent virtual circuit, some network administrator configures the connection state. Right? So this is a static approach. And also it's problematic if the size of the network is not small, right? And because it depends on manual configuration, these are typically long-lived, right? The other approach, which we are going to discuss in detail, relies purely on signaling, right? So a message from host basically configures the connection state, right? So host sets up and deletes virtual circuits dynamically without the involvement of network administrator. Now we are going to see how a virtual circuit is established using signaling. And for this we are going to use the example that I showed you before. And again, to remind you, what we're going to discuss would have host A as the source and host B as the destination. And clearly the path from host A to host B is from host A to switch 1, and then from switch 1 to switch 2, and from switch 2 to switch 3, and finally to host B. So the first thing that host A does is that it sends a setup message to switch 1, and this setup message has the address of host B as the destination. And the result of receiving this setup message is that switch 1 will create an entry in its virtual circuit table. And it's the same example that we saw before. So this virtual circuit table entry would have 2 as incoming interface, because host A connects to switch 1 via interface 2, and switch 1 would allocate a virtual circuit identifier that is unique on this incoming interface. And so in this example it finds that number 5 is not used, so it assigns number 5. And again, we have to assume that switch 1 knows how to route this packet to host B, and we will come to routing, as I said, in few lectures, but for now just assume that switch 1 knows how to route packets to host B. And so it knows that this incoming packet has to be forwarded on interface 1, right? So the outgoing interface would have 1, and then it leaves this entry of outgoing VCI empty, because that is going to be assigned by switch 2, and switch 1 has no idea of which identifier is free at switch 2 on this incoming port. That knowledge is only with switch 2. And so after that it forwards the setup request to switch 2, and switch 2 itself would have would add an entry in its virtual circuit table for this setup request, and that suppose looks like this shown here. So the incoming interface is going to be 3, because that's how switch 2 is connected to switch 1. And now switch 2 finds that identifier 11 is not allocated at this interface, so it allocates number 11. And then again it knows that this has to be forwarded to switch 3, and that is connected on interface 2, so it would have number 2 in its outgoing interface field, and then outgoing VCI is going to be empty. And after that it's going to forward this setup message to switch 3. Switch 3 is going to do similar things. So again, incoming interface 0 finds a free VCI number 7, knows that it has to send on interface 1, then leaves this outgoing VCI empty, and then forwards it finally to host B. Assuming that host B is running and it is willing to accept packets from host A, it's going to send an acknowledgement message back. And in this case, the host B assigns the virtual circuit identifier number 4 for this request. So this 4 that switch 3 got from host B is going to be put in its virtual circuit table, right? So this would look like that. Then switch 3 is going to forward this acknowledgement message to switch 2, and that would indicate this circuit identifier that switch 3 assigned to this circuit, and that is going to be number 7. So that is going to appear here. And then switch 2 again forwards this acknowledgement to switch 1, indicating that it has allocated number 7 as the identifier. And then switch 1 puts this number 7, and let me just go back, sorry, number 11, I'm sorry. So this is going to be not 7 but number 11. And then lastly, switch 1 would inform host A to use the virtual circuit identifier number 5 for this connection, right? So this acknowledgement comes back to A with an indication that it is supposed to use VCI 5 for this connection to host B, right? So this is summarized here. This virtual circuit table entries at all these switches again in complete form look like this. Now once A is done transmitting to B, the connection has to be torn down. For tearing down the connection, A sends a tear down message to switch 1. When switch 1 receives this message, it deletes this relevant entry from its virtual circuit table and forwards the message to other switches in the path, and every other switch does the same. So basically they would delete this entry from their virtual circuit table. At this point, the circuit no longer exists, and so if host A sends a packet with VCI 5, and when it's received at switch 1, it's simply going to drop it, right, as if this connection had never existed. In the case of virtual circuits, since the sender has to wait for the connection request to reach the far side of the network and return before it can send the first data packet, there is at least one round trip time delay before data is sent. Second, if a switch or link in a connection fails, the connection is broken and a new one will have to be established, before the data transmission can continue. And another characteristic of virtual circuit is that by the time the host gets the go ahead, means the acknowledgement of the setup request comes back to it, it knows that there is a path to the receiver and that the receiver is willing to receive data. In comparison, Datagram network has no connection establishment phase, and therefore a start of data transmission can happen immediately. There is no one round trip time wait. And second, each switch processes each of the incoming packet independently. So it's possible that different datagrams take different routes. Another thing is that in the case of datagram switching, each arriving packet competes with all other packets for buffer space. So if there are no free buffers, the incoming packet has to be dropped. In contrast, in the case of virtual circuit, it's possible to allocate resources to the virtual circuit at the time it's being established. So we may allocate buffers to circuits so that at least they don't compete with other flows for buffer space. And it is also possible to do hop by hop flow control. And lastly, in the case of virtual circuit, we can provide quality of service to individual circuits. Right? So we may allocate bandwidth to circuits, or we may assign priorities to different circuits, so that a circuit with higher priority has its packets forwarded on a priority basis, so they wait for shorter duration in queues. X25 network was a successful networking technology back in the days. It is obsolete now, and X25 used virtual circuit switching. In X25, when the circuit was being established, right, buffers were allocated to each virtual circuit. Secondly, a sliding window protocol was run between each pair of nodes. And then this sliding window was augmented with flow control, so that the receiver could prohibit sender from sending data at a higher rate than it can possibly process. And lastly, the circuit setup request was rejected, right, if a node didn't have enough buffer, right, when the connection request message was processed. Another networking technology where virtual circuit switching had been successfully used is called ATM, or asynchronous transfer mode. This is a connection-oriented packet switched network. In this network, packets are of fixed size and they are called cells. So each packet has a 5-byte header and a 48-byte payload. All in all, 53 bytes. The designers of ATM chose fixed cell size, right, of 53 bytes because it turns out that fixed length packets are easier to switch in hardware and design simpler hardware to do. Let us look at ATM cell format. So the fields of interest are these two fields primarily. So first is called virtual path identifier, and the second one is called virtual circuit identifier. The virtual path identifier is 1 byte wide and virtual circuit identifier is 2 bytes. So VPI and VCI combined is what we had been referring to as VCI in our discussions. In ATM, they are divided into two pieces to enable hierarchy. So circuits with the same VPI are routed similarly. And within a single VPI, different circuits are identified using different VCIs. And note that the payload is a fixed size, as I mentioned before, it's 48 bytes. There is some more discussion of ATM in the textbook. The third switching approach that we are going to discuss is called source routing. In source routing, the information that is required to switch a packet is provided by the source host, and that's why this name, source routing. And there are two kinds of source routing. One is called strict source routing, other one is called loose source routing. In the case of strict source routing, the entire path is specified by the source. In the case of loose source routing, a subset of nodes are only specified by the source routing, and the network is free to choose other nodes. Here is an example of strict source routing. So again, message is originating at host A and it is supposed to be delivered to host B. And in this case, what host A is doing is it's identifying the ports at which its packets are to be forwarded to by each of the switch that is encountered on the path. And this is to be read from right to left. So when switch 1 receives this packet, right, so it's going to look at the rightmost entry, and that's 1. So this is going to be forwarded on interface 1, right, that would take it to switch 2. And before doing that, it's going to rotate these entries. By rotation we mean that the first entry goes to the last, second goes to first, the third goes to the second, and so on, right? And so now the route sequence looks like 0, 3, and then 1. So switch 2 is going to look at again the rightmost entry, and it says 0, so it's going to forward this on its port 0, right? And again, before forwarding, it's going to do this rotation, right? So 0 is going to go in the third position, 3 is going to go in the first position, and 1 is going to come back to the second position. And then again it comes to switch 3. Now the rightmost entry is 3, and so switch 3 forwards it on its interface 3, right? And this message reaches host B. Note that when host B receives this message, right, this would have been rotated back. So 3 goes to third place, 1 goes to first place, and 0 goes to second place, right, which is exactly what host A had sent. And so the benefit of having this entire route at host B is that now it knows how to send this. If it has to send an acknowledgement back or response back, it knows how to reach host A. Here are some other approaches shown. So we have seen this first approach where we rotate the entries. So this is, suppose this is the header at the time of entering the switch. So when this message is leaving the switch, the header is going to look like, so this B is going to be rotated to first place, C goes to the second, D goes to the third, and A A goes to the fourth place, right? And so this is what is shown here. In another approach, what we could simply do is that once the message is leaving the switch, then the rightmost entry is removed, and so at the time of leaving the switch, the header would look like just this. So DCB is still the rightmost entry, is the entry that the next switch is going to look at. And here is yet another implementation where we have a pointer that always points to the entry, right, that the switch is going to look at. So at the time that this packet is arriving at the switch, right, suppose this is pointing to this entry A. Now once this is leaving the switch, right, this pointer is going to be manipulated such that it now points to the second entry. And so again, with this second approach, we lose this benefit that host B would know how to reach host A, because by the time this message reaches host B, the path from A to B, that information would be gone. And these two approaches actually preserve that information. One downside of source routing is that the header length becomes variable. So the longer the route, the longer the header. To summarize, we saw that by interconnecting switches, we can build larger networks. This is the first thing we learned in this video. And we also saw that switched networks are more scalable than shared media networks, because unlike shared media networks, in the case of switched networks, hosts are connected to switches using point-to-point links. Then we saw three approaches for switching. The first one was datagram switching, the second was virtual circuit switching, and the third was source routing. Datagram switching is a connectionless switching approach where you make the forwarding decision based on the destination address present in a packet, and it's done on a packet-to-packet basis. In the case of virtual circuit switching, a connection is established before data transmission takes place. And what we mean by establishing connection is that while establishing connection, switches would make an entry in their virtual circuit table, right? That means they maintain states for forwarding. And lastly, in the case of source routing, we saw that the path to destination is specified, either fully, we saw an example of that, or it's possible to do it only partially. And this specification of the route is done by the source node. The material that we covered in this video is discussed in detail in Peterson and Davie, chapter 3, section 1. And bits of this is also discussed in Tenenbaum and Weatherhall, chapter 4, section 8. That's all in this video. See you next time.